Dear students, in this session we are going to see about the torque due to an electric dipole placed in a uniform electric field. That means when the electric dipole is placed in the external electric field, that electric field is a uniform electric field. So that means very simply, when the dipole placed in an external electric field, what it will be happens. So what is the meaning of uniform electric field? Uniform electric field means the electric field line, the space between the each electric field lines will be same. So that is called as a uniform electric field. And this picture shows that the external electric field E and the dipole will be placed in the external electric field. This is a plus Q charge, this is a minus Q charge. So due to this external electric field, this plus Q charge experience a electrostatic force. So that force equation is F is equal to plus QE, and similarly the negative charge minus Q also experience a electrostatic force. That equation is F is equal to minus QE. So this plus QE and minus QE, the magnitude is equal because this Q and this Q are equal, because dipole definition is, what is electric dipole? Two equal and opposite charges. So the magnitude of the Q, both the charge plus Q and minus Q will be same, and also this is a uniform electric field. That is, the electric field at this point and the electric field at this point are same. So this F is equal to plus QE and F is equal to minus QE magnitude, that means the value will be same. Hence it is a equal and opposite. The total net force on this electric dipole is equal to 0. The net force on this electric dipole placed in the external electric field, external uniform electric field, is 0. So you see that this force will pull this side, this force will pull this side. So what will happen? This is a electric dipole. So what will happen when the force, one of the force will be pulling this side and another force is pulling in this direction? This dipole will set to rotate. This rotating force is called as a torque. So the torque is a moment of force, the moment at which the dipole is rotating. The definition of the torque is the force into perpendicular distance. So the torque is, what is the torque? Torque is the force into perpendicular distance. Then it is represented by the term tau, which is equal to, what is the magnitude of the electric force? The magnitude of the electric force is QE and the perpendicular distance is BC. How it is BC? Now you see the picture. So this is the electric dipole. So I draw the imaginary normal line, perpendicular line from the dipole. So positive charge of the dipole, so it will be connected with the negative charge of the dipole. This perpendicular distance is called as a BC. This is a perpendicular distance. So this shows one right angle triangle. This is a 90 degree. This is an angle theta. So in order to find this length, what is this length? We already know that this, what is the distance between the two equal and opposite charges in an electric dipole? Yes, this is 2a. Hence AC is equal to 2a, and what is BC? That can be calculated by using sin theta formula. Sin theta, which is equal to opposite side by hypotenuse. What is the opposite? The side which is opposite to the theta is called as a opposite. So this is the opposite, BC. Then hypotenuse is this one, 2a. Hence BC, which is equal to 2a sin theta. The students may ask one question: why, sir, we are not put any cos theta here? If we put cos theta, we get only adjacent side by hypotenuse. We need only the perpendicular distance, not this AB distance. Hence we are using the angle sin theta. So BC, which is equal to 2a sin theta. By substituting this BC as a 2a sin theta, we get that QE into 2a sin theta. Hence the next step is Q into 2a, which is into E sin theta. Since we know that Q into 2a is a dipole moment, P. So you substitute this P value here, we get the equation, the torque tau is equal to PE sin theta. This PE sin theta can be written in vector form. That is, torque is a vector quantity, dipole moment is a vector quantity, then electric field is a vector quantity. So we can write this equation, this PE sin theta as a P vector cross E vector. Sir, what is this cross, sir? We already know that when the two vectors are multiplied, the products are two types of vector products. One is a dot product, another one is a cross product. When two vectors are multiplied, if you get the scalar, that is called as a scalar product. We have to write that A vector dot B vector is a scalar product. We get the answer AB cos theta. But for vector product, when two vectors are multiplied, we get a vector, another vector quantity, then only we have to use the vector product. Here, the dipole moment is a vector, electric field is a vector, hence we get a torque. Already we know that it is evidently, we know that in the lower class 11th standard itself we studied tau is also a vector quantity. Hence we are using the vector product. Tau is equal to P vector cross E vector. This is a equation for torque due to an electric dipole placed in a uniform electric field. The very important thing is the net force on the uniform electric field is 0, but the net torque is not equal to 0. Now we are going to see about what happens when the electric dipole is placed in a non-uniform electric field. Already I told that uniform electric field means the space between the electric lines are equal. But for non-uniform electric field, the space between the electric field lines are not equal. It is not intersecting. It is going in this direction. So you see that this left side, the space between the each electric field lines are bigger than that of the right side one. Hence we come to the conclusion, when the electric field lines are far apart, the field strength is very less. That is a decreasing electric field. Here, when the field lines are very closer, it is a stronger electric field. We can write it as a increasing electric field. Now you see that this is an electric dipole plus Q minus Q separated by a distance 2a. So there is a force F is equal to plus QE. There is another force in this side, that is F is equal to minus QE, similar to the uniform electric field. So here the one force will be pulling this side, that is a Q into E. E is a increasing electric field. The strength at this point, electric field value is higher than that of the electric field at this point. So this force is greater, this force is lesser. Hence the net force, the total force is not equal to 0. So we can write that for the electric dipole in a non-uniform electric field, the net force on the dipole is not equal to 0. But for uniform electric field, it is 0. And since we should take that net torque is also not equal to 0. Now I take the one simple diagram to explain this concept. This is electric dipole minus Q plus Q. So the dipole moment always directed towards from negative charge to positive charge, and electric field, this electric field is not an electric field of this dipole. This is an external non-uniform electric field. So this is a non-uniform electric field. So the so you see that the negative charge force is F is equal to minus QE in this direction and plus QE in this opposite direction. So where it is a more electric field, this direction is a more electric field. Hence we come to the conclusion, when the dipole moment and the external non-uniform electric field direction are parallel to each other, both are in same direction, when the angle between them is theta is equal to 0, then the total net force on this electric dipole, already I told that the net force is not equal to 0. So what is the direction of this total net force? That will be directing towards the increasing electric field, where the applied electric field value is more, that direction only this electric dipole force will be acting. Similarly, when the dipole moment and the external electric field are anti-parallel, that means 180 degree, simply I will change the dipole. This here is a minus Q, here plus Q, here the plus Q and minus Q, it will be interchanged. Hence we get that dipole moment direction is in the opposite sense. It is from the negative to positive charge. When the angle between the dipole moment and the electric field is 180 degree, that is anti-parallel. Hence the net force direction, the dipole moment net force direction is acting towards the decreasing electric field. This is a very important point. Very simply, students, don't confuse with that. Simply you remember that when the dipole moment and the electric field are parallel in the non-uniform electric field, the dipole moment force direction is along the increasing field, and when it is anti-parallel, the dipole moment force is along decreasing electric field. Here the torque, we will say that are equal to 0. But in this, that is, it is a generalizedly net torque is not equal to 0. But for these two cases, when the dipole moment is other than these two positions, that is a parallel and anti-parallel positions, remaining positions only, net torque is not equal to 0. When the dipole moment is in 0 degree and 180 degree with the external uniform non-uniform electric field, then the net torque is equal to 0. Note down this point, students. This may be asked in exam point of view.